Okay, so we've got a mass of particle of mass 0.3 kilograms moving at this pace, and after an impulse it has here, so there's an impulse going between this. I need to do this with an impulse momentum triangle. Now I know that impulse equals the gain in momentum, so that's final momentum minus the initial momentum. More than that, I know that momentum is mass times velocity. But I don't like doing a velocity, a vector triangle with a subtraction. I want an add, so I'm going to add this to the left-hand side, and so I'll get impulse plus the initial momentum equals the final momentum. And in order to do this, I've got these two arrows, so I associate them with vectors and with arrows. These two arrows, from the beginning of the first one to the end of the second one, must equal the final momentum from the beginning to the last. So initial momentum, I can put that on that. That's dead easy. That just goes across there. Momentum, mass times velocity. So 0.3 times by 0.4. I can't put the impulse on here because I don't know where it goes. I know it's got to start off from here, but I don't know in which direction it goes or how long it is, because that's what I've got to find. But I do know that the answer, the final momentum, must start here and must go, well, it actually tells me, 30 degrees, so it's got to go at 30 degrees to this, and it's got to go 0.6. So if I draw it 0.6, this means the impulse, the momentum here will be mass, which is 0.3 times by 0.6. And as you can see, 0.4 is here, 0.6 is going to be longer, so I'm going to make sure this goes longer than that. So I can do it a bit to scale. And that's the final momentum, is that bit there. And so now I can have the impulse must go here. So that will be my impulse. And once I've got that, I can now work out what the impulse is, because I've got a triangle here and I've got use the cosine rule. So I know that I squared will equal, what's this? That's 0.18. The easiest to do it, and that is 0.12. So that will be 0.18 squared plus 0.12 squared minus 2 times 0.18 times 0.12 times by cos 30, and that gives me that I squared equals 0.00938 whatever, and that means that I equals 0.096890157. Don't need quite that accuracy. It doesn't seem very much, but then again we got 0.12 here, and now we've drawn a diagram. It does seem reasonable, even from our diagram, that it's a little bit less than 0.12, and indeed it is. So we've got to check, because we've done a rough scale here. What I need to find, I've worked out the magnitude of the impulse. I need to find the angle its line of action makes with the original direction. Well, the original direction is here, and so I've got to work out this angle there. But actually, so I'm going to use the sine rule to work out this one. And you'll see when I do the sine rule, that is definitely an obtuse angle. Okay, so let's just do that. I'll do it up here. So I've got, let's call it x. I've got sine x over 0.18 equals sine of 30 over what I've just worked out, 0.09689, etc. So that tells me that sine x equals 0.9288, etc. And so x equals sine to minus 1 of that equals 68.26 19662 degrees. Well, it can't be, because that's meant to be obtuse. Or, for when sine goes, it's 180 minus that, minus 68.26. It can't be that. For x, it must be this. But that works out this angle, and we want direction of motion, so we want this one here. So what the angle we want, angle we want is 180, because it's on a straight line. 180 minus the angle we just worked out. So it's 180 minus that angle there. And so that angle equals 68.2619 degrees. We're putting dot dot dot, so it's not rounded that properly. Okay, part 2. State the impulse. Suddenly a second impulse acts on P. After the second impulse, P again moves left to right, so it's gone back to where it was with speed 0.4. So it's slowed down and gone back to things, and it's parallel to its original direction of motion. Okay, and that means that the magnitude will be the same as before. Same as before. And I've got to show the direction on a diagram. Well, the direct thing is, it was coming like so. That's the 0.3 times 0.6, and it's going to go in the opposite direction, back like so, and that'll be the impulse in opposite direction to before. And to explain that a little bit, if I think about this impulse as two components, as that component and that component, well, in order to get it to slow down again, we need to change the horizontal components by the opposite of this, because this increased it from 0.4 up to 0.6 cos 30. It's got to slow it down, so I've got to have a component going backwards, and equally it's increased the momentum up here, and now I've got to decrease the momentum, so it's got to go back there. So those two components, which is why it goes in exactly the opposite direction.